All right, this last video is just talking about some different wave behaviors. This is actually the third page of the wave notes that you have. As it says on the screen, basically there's four things that can happen when a wave runs into something. Sometimes it does all four at once, depending on what kind of barrier it's running into, but the wave can either reflect off of the barrier, it can do what's called refraction, which this is an image of that, we'll explain that in a minute. It can do diffraction, it can diffract, or it can be absorbed into that barrier. Again, what happens at that barrier depends on what kind of wave we're talking about, depends on the energy of the wave, and it depends mostly on the type of barrier that we're talking about, the shape, the material, all that stuff. So let's talk about each of these four in turn. Reflection first. Reflection is probably the one that you're most familiar with. It's simply when a wave bounces off and goes in a new direction. You can see a picture of that here. Any wave does this, whether we're talking about sound waves, light waves, water waves, any kind of wave does reflection. It bounces off of the barrier and it goes in a new direction. The wave that reflects is just like the original, exactly like the original. It's simply moving in a new direction, right? So example that we have here, mirrored sunglasses. Those are glasses that have that kind of metal coating on the outside, and you can see yourself in them when you look at someone else and you kind of feel weird about it. But any mirror, any when you see reflection in water, all of that is simply reflection of light. Sound bounces off of a wall, that's reflection of sound. And so we have what's called the law of reflection, which actually is not in your notes, but you will need to write it down, and it's seen here. It's very simple. It's not really even an equation that you need to worry about. It just says that the angle of incidence is equal to the angle of reflection. That means as the wave comes into the barrier, it's reflected out at exactly the same angle. Now the angles are measured with respect to a line called the normal, and this line is always perpendicular to the surface. And you need to know that because we're going to refer to the normal again when we talk about refraction. But the line is called the normal because normal means perpendicular. So you can just imagine that there is a little square right here between the normal and the surface because the normal is perpendicular to the surface. And so now that we have that normal drawn, we can measure the angle of incidence and the angle of reflection, because these angles that we're going to talk about, both dealing with reflection and refraction, are always measured between the normal line and the ray, or the line that represents the wave coming into the barrier. So this is the line that represents, let's just say this is light, represents the ray of light. So the angle is measured in between that ray and the normal. So this is the angle of incidence because this is the incident wave coming into the barrier. And this is the angle of reflection right here because this is the reflected wave coming off of the barrier. That's the law of reflection. It's very, very simple. The angle of incidence equals the angle of reflection. Okay, and you have to measure those angles in reference to the normal. So refraction looks like this. If the termination of the medium is free to move, as is depicted here, imagine this is a ring on the end of a rope, and perhaps this ring is tethered to a pole, and this ring is allowed to move up and down. If that's happened, the wave reflects in phase, and in phase means when it goes in as a crest, it'll also come out the same as a crest. And so the reflected pulse would look like this. It would come this way and it would reflect back as a crest. And so you have a bunch of crests reflecting this way. But if the termination of the medium is not free to move, that means it's fixed in place, it can't move, the wave reflects out of phase. That means if it comes in as a trough, it comes out as a crest, or vice versa. Okay, so if the wave is free to move, the wave reflects. If the end of the medium is free to move, the wave reflects in phase. If the end of the medium is not free to move or fixed, it'll reflect out of phase. Okay, so that's reflection. The only thing you needed to add to your notes again is this law of reflection, which is actually very simple. Let's talk about refraction now. Refraction happens when waves cross a boundary between two different media. I want you to underline or circle this part right here. The two different media is the most important part of this. When light goes from one medium to another, it changes speed. Remember that The speed of a wave is determined by the medium. And that's really important because when light changes speed, it actually bends. And I'll explain why in just a minute. But this happens with eyeglass lens, with prisms, with many, many things, any kind of lenses, teardrops, drops of rain. Refraction is the reason why you get rainbows, because the light is refracted through a drop of water. Each drop of water is like a tiny little lens or prism. So refraction happens because light waves bend, or sound or anything else, but this is most pertinent to light. Light waves bend when they cross a boundary between two different media. All right, so I want you to imagine that you're driving in your car and this is your aerial view of your car. You're moving in this direction, okay? And you're on the side of the road, and let's just say you fall asleep. This is concrete, and let's just say this is gravel, very loose gravel over here on the side. All right, you fall asleep and your wheel inadvertently turns in this direction. Your car begins to move in this direction. Okay, you're going to move off the pavement. All right, let's actually get down here to picture this so we have some more room. Here's your car. You're going to move off the pavement. All right, let's picture your tires. All right, the tires of your car. I'll move a little bit closer. Tires of your car from the air look like this. And as you can see, as your car begins to go off the road, what you might notice, I hope you notice right now, is that not all of your tires contact the gravel at the same time. In relation to refraction, this is two different media, right? This is the media that we're coming from, the medium that we're traveling from, and this is the medium that we're traveling into, concrete and gravel. It's not exactly the same as waves, but it's very similar, all right? So if we imagine that in this case, your front right tire will be the first one that crosses this boundary into the new medium. And the rest of the tires are still on concrete. Question is, in which medium can you move faster? And I think it's quite obvious with a car that it's faster, it's easier to move in the concrete. When you move onto gravel, your car is going to start slowing down because gravel, your tires will sink into the gravel a little bit more, and your tires are going to go slower. But the problem is, this tire begins to move slower, while these other three are still moving at the same speed. So you have one tire that's moving slow, and the other ones that are moving very fast. And what happens is, when this one's moving slow and this one's moving fast, what you end up getting, you might have done this before, like when you're pushing a grocery cart through the, somebody texted me, y'all quit texting me. So when you're pushing a grocery cart through the store, and maybe you hit like a piece of paper underneath the wheel right here and it locks the wheel, you might notice that immediately what happens is the grocery cart pulls to the right. It pulls to the direction that the wheel is locked. Well, the same thing is going to happen here. This wheel slows down while this one's still going the same speed. So what you get is, instead of your car moving in a straight line this way, your car is going to pull in the direction of the slower moving wheel. So your car actually ends up moving in this direction, right? Your car changes directions. If you don't grab the wheel and change the direction of the car, it's going to change directions because different parts of your car are contacting the new medium at different times. You don't cross into that new medium at the same time. That is the key here. And a light wave is much the same way. A light wave is actually a transverse wave, so you can think about it like this. The deal is, and remember that a light wave is a double wave like this. The point is that since a light wave is three-dimensional, it's the same concept. Not every bit of the wave contacts the new medium at the same time. For that reason, it's going to bend, and it bends in the same way that your car bends. Imagine that there is a normal line that's perpendicular to the boundary layer. It would be here with the light wave. It would be here with your car, perpendicular to the layer. Your car will always bend toward the normal if it's moving into a slower medium. And it would do the very opposite if you're going this way. Your left front tire would contact first if you're moving back onto concrete. Well, in this case, this one's going to start to go faster. So instead of moving in a straight line this way, you're going to move in the direction of the slower wheels. You're going to pull this way. So your car is actually going to help you out and pull you back onto the road this way. This is the normal line. Notice what's happening. As your car moves into a medium that's slower, it bends toward the normal line. So instead of going straight, it bends in a direction that's toward the normal. But if it's moving into a medium that's faster, it bends actually away from the normal. So it looks like this. Same thing with a light wave. When a light wave travels into a new medium, instead of moving in a straight line, it will bend toward the normal if it's slowing down. All right, let's look at this on the PowerPoint. So when a wave enters a new medium where it has a slower speed, with light, this is a less optically dense medium. For example, that could be light going from air into water or air into glass. What that means is that it shortens the wavelength, the frequency stays the same. We're going to talk about all this more in detail later. All you really need to know right now is that the light wave will bend toward the normal. So you need to write that down, that the light bends toward the normal when it slows down. And we're going to talk about this again later. But vice versa, what happens when when a wave enters a new medium where it has a faster speed? So that's opposite. For instance, light waves going from glass to water or water back to air. Anything where it's speeding up, the light wave will bend away from the normal. So if it slows down, it will bend toward the normal. If it speeds up, it bends away from the normal. That's the reason why refraction happens. Refraction is the bending of waves when they cross a boundary layer. And this is the reason why the waves bend. And there's a lot of other things that happen when the waves bend, but refraction is the bending of light waves when they pass a boundary layer. Diffraction is the next one. Diffraction is easy. It's the bending of waves, not when they cross a boundary. These waves are actually in the same medium. Notice the medium doesn't change here. They bend when they go around the corner of a barrier here. Really good example of this is that you can hear someone in the hall even when the door is open only a tiny crack, because the sound waves don't continue to travel in a straight line. They actually bend around that medium so that you can hear someone in the room. The sound waves bend and move into the room around the barrier. Same thing with water waves. If you have water waves going into a barrier like this, there's only a small opening here. Well, the waves aren't going to move just through this opening and continue in a straight line. They're going to bend around the corner of that opening, both directions, and they're going to radiate out in all directions. And so you get this circular wavefront pattern as the waves move past the barrier. So that's the example that I want you to draw of refraction there, or diffraction rather. So we had refraction is bouncing, reflection is bouncing. Refraction is bending of light waves as you cross from one medium to another. Diffraction is the bending of a wave as it goes around a corner of a barrier. So we're not changing mediums here. The last one is simple. It's absorption. A light wave or a sound wave or any other kind of wave can be absorbed. That means the wave gets smaller in amplitude as it travels through a boundary. Waves can actually travel through boundaries that are porous. For example, a heavy curtain might absorb sound, or there are specific rooms that are designed to absorb sound waves so they don't get out. You can have a soundproof room. I'll link a video actually on this page where the videos are that talks it's a really good video from Veritasium about a soundproof room. Dark glass or dark colors simply absorb light waves. Light waves, when they contact a barrier, they can either be absorbed or reflected, and many materials simply absorb certain frequencies or colors of light waves and reflect other frequencies or materials of light waves. All right, so that's all you need to know about the four behaviors of waves. Again, we had reflection, we had refraction, diffraction, and absorption. There's four behaviors of waves.